So today I will talk about some of the recent work I did with Nathan Weeb from University of Toronto and Carlos Ortiz Morero from Pacific Northwest National Lab. So over the last few years, similarly to Juan Miguel, I've been interested in quantum machine learning and whether or not we can actually do some interesting machine learning task on a quantum computer. And today I will give you some of my musings about what I think are some of the maybe misconceptions when people think about quantum machine learning. And also, I will tell you where I think quantum QML really has the chance to shine. Then I will talk about some of the issues with training quantum neural networks known as Barron plateaus. And I'm sure I'm not the only one person at this conference talking about difficulties of training QNNs. And lastly, I will talk about this really weird new quantum algorithm that my colleagues and I thought about and why we think it might be interesting for other people to hear. So usually when you hear the pitch for QML, it usually goes as follows. Well, we know that quantum computing is very powerful. It can solve problems such as factoring in a polynomial time, even though these problems might be exponentially difficult for classical computers. And machine learning is also a very powerful technique that we are using in our lives very often. So if I want to find out what's the weather, I will just say, hey Google,
or I connect to the Wi-Fi network. You might want to check the connection settings in the Google Home app.
Well, and sometimes it works. And so it just really makes sense to put these two powerful techniques together and see if we can get something much better out of it. And over the recent last 2 or so years, we've been getting some strong indications that this might be, in some cases, very, very powerful. There was a very recent experiments that people from Caltech and Google performed that showed some quantum speed up. There were results from peg learning showing that quantum in some case needs much fewer samples. But in many cases, we don't really know whether when we combine quantum and ML, if these two techniques would go together well as, let's say, cherry pie and vanilla ice cream, or we can also combine them in a way that we will create a monster where all the individual parts just hurt each other. Sorry for the Americans in the audience who might think that a donut burger is absolutely delicious. I don't really share your opinion. But quantum machine learning is really, really hard to really explore and understand. And this is because an algorithm needs to be seen to be believed. And with quantum, we don't really have large quantum computers yet. To really run any serious data science task, we would need massive computational power in either classical and quantum. And with the number of qubits that we have right now, it's really, really difficult to it's usually impossible to perform any serious data analysis, either with classical or quantum data. So doesn't mean that we need to wait until we get a really big quantum computer to start exploring quantum machine learning. Well, I don't think so. There are still lots of things that one can do. And one of these things is theoretical analysis. Either without a quantum computer, we are still able to show a lot of things that quantum computers wouldn't be good at. We have the tools of computer science and complexity analysis to say that some tasks will be just really, really difficult, even for quantum computers. And we can also come up using just the formalism of quantum mechanics with some really nice tricks and ideas that will allow us to create quantum algorithms once we have these bigger quantum computers. And we can also do some small instance demonstrations. Numerically, we can simulate systems with with handful of qubits that don't always generalize into bigger systems, but they still can give you, some feel for what works or especially what doesn't work. There are also NISC devices where we can test some of these ideas and run them on actual hardware. But right now, we are very limited by noise. So these are all different approaches that are all valid depending on what the exact methodologies you would be using. But in my work, I usually focus on the theoretical analysis. I like to compute bigger complexities and write some theorems. So in quantum machine learning, one way how we can think about processing data on the quantum computer is that we take some digital data, prepare it in encode it in some quantum state, and then process it on a quantum computer. And the hope is that maybe if using quantum computer, we could have a much richer class of models that we would be able to work with. And this could maybe give us faster algorithms. However, this is quite difficult to do. What we can do instead, and again, I don't think I'm the only person talking about these ideas right at QHack, is to learn directly from quantum states. And this is because getting information from quantum states is quite difficult. To describe a quantum state perfectly, one would have to do full tomography, which is exponentially expensive. But very often you might not need to do full tomography. And there are some property of quantum states that we can learn directly if we have the ability to process them either on classical or on if we have the ability to process them on a quantum computer. So I'm very interested in this now fully quantum machine learning, where either we learn directly from quantum states and process it on a quantum computer, or we can also have some input that is either quantum and classical, and our goal would be to learn to generate some quantum states. So we would be learning some generative model, and that would allow our quantum computer to prepare quantum states from some family of states. For example, some ground states or some terminal states, which I will talk about later. Many of the models we have in QML are based, albeit very loosely, on classical ML models. And one of them is this quantum version of a feedforward neural network. So in a feedforward neural network, we would be the data would go through the neural network, and our goal would be to learn some weights and biases. In the quantum case, instead, we will be learning parameters of quantum gates. So our unitary quantum neural network can be seen as a parameterized, can be seen as a quantum circuit with some parameterized gates. In this talk, all the gates will be parameterized as some simple rotations where the individual Hamiltonians Hj are given, but our goal will be to learn the individual angles theta j, or you can think about them as time in Hamiltonian evolution. In this type of a network, we will qualify how good our model is, how good our quantum neural network is, by looking at the objective function. So this is the same as a loss function. And generally, people do it by measuring some Hermitian observable on a subset of qubits. As my picture shows, we don't always need to measure all the qubits. We can have some ancillary qubits, and I will refer to these as hidden units to align better with the nomenclature of classical neural networks. And the units where I will be measuring the objective function on will be called visible units. So the goal here would be to learn to parameterize the unit array to minimize the objective function. So the really big question is if we can efficiently train these models. Because you can have a model that is very, very powerful if it's properly trained. But if you cannot train it, then this is not especially useful. So the most common type of training is some type of gradient descent. So you might be familiar with stochastic gradient descent. To perform these types of gradient descent trainings effectively, we need to have two components that will be both efficient. So first, every time we are estimating gradients, they need to be efficiently computable. Usually we don't care about having the gradient exactly, but we need to be able to compute its estimate in a reasonable, which I mean polynomial number of steps, polynomial number of gates, also polynomial number of measurements. And second, we really care about the convergence of our gradient descent algorithm. The number of steps that we will need to make to get somewhere close to the global minimum will need to be at most polynomial. So how would it look like in Uluru, one of the most famous places in Australia? When we are in some place in this landscape, the gradient will be point in the direction of the steepest descent. So we start on the rock, where we can look at the gradient all around us and determine that we need to go, as the arrow suggests, and then we will be going down. However, we can also find ourselves anywhere in many places where the gradient will be zero or effectively zero. And in that case, there isn't really any place that is lower or better than our current spot, and our gradient descent algorithm would get stuck. And if this happens, we say that we are in a barren plateau. Barren plateaus are extremely common in quantum neural networks. They were first described by Jared McLean and a team from Google as they emerged in deeper circuits. Then Marco Cerezo and other folks from Los Alamos showed that you can also see barren plateaus with shallow circuit if the cost function is what they call global. And my colleagues and I show that if we have many, many ancillary qubits, they can become entangled with our visible qubits, and this entanglement can also cause a barren plateau. Also, what is really important to realize that unlike vanishing gradients classically, quantum algorithms typically start at a barren plateau. So you initialize your model, it's absolutely horrible, but immediately it starts in a barren plateau, and that means that it's not learning. It starts bad and it stays bad pretty much forever because it's not really able to converge to anything better. And recent work from Zoe Holmes shows that these barren plateaus are actually a really, really big problem because in QML, one would need to choose between expressivity and trainability. So these authors show that if we have a model that would be very expressive to capture intricacies of many of difficult problems in quantum computing, then these models wouldn't really be trainable efficiently under some in their very reasonable definitions. So the key question is whether there is any way out. Is there something we can do to leave a barren plateau, or even better, to never enter it? So my colleagues here and I carefully looked at the assumptions of all the parent plateau results, and uh, we realized that not only the parent plateau is determined by the number of visible units, hidden units, or the number of gates here. The term that also comes up is that the objective function that we would be measuring is usually thought of as bounded. But if you look at on the classical side, people use the KL divergence or negative log likelihood as their objective functions, and these objective functions are unbounded, and they also have simple gradients. So our goal in the work that I will talk about now was to find an objective function that would be unbounded. So it would violate the assumptions in all these barren plateau results. And also we try to find something that would have simple enough gradients. So to really bring this point home, let me just stress that the barren plateau rule theorems, as we know them, don't apply to unbounded objective functions, even though almost all the quantum machine learning that people use now uses bounded operators. So let's talk about the classical machine learning machine learning objective function for a moment. So KL divergence is the most common objective function, and it very roughly tells you what information we would be losing if we about the loss of information if we replace our data by a model. And because of the logarithm down here, the KL divergence can become very, very large. However, KL divergence is computationally difficult to compute. Knowing exactly how good your model is would take an exponential amount of resources classically and, well, also quantumly. However, what people use in classical ML is that they never really evaluate the objective function. They only look at the gradients, and those can be estimated through sampling. Are there any analogs of quantum KL divergence? Well, yes, there are. And the direct analog of KL divergence in quantum world is quantum relative entropy. You could see that it has the if you spend some time studying quantum relative entropy, you could show that it has the same information theoretic meaning as KL divergence, but in the quantum world. However, computing the gradient can become very difficult because of non-commutativity. So if you have a model with no hidden units, quantum relative entropy would be just fine for training. But once you introduce any hidden units, and probably you want to have some, quantum relative entropy is not the best objective function because the gradients are just a pain to work with. So instead, there are also many other types of entropies and divergences that you might want to work with. So we'll look over some information theory textbooks, and we saw that we learn about the maximal quantum Riemann divergence for alpha equals 2. And this is not really the most catchy name for an objective function. So if you have a better name for this expression, please let me know later. But what we really like about maximal quantum Riemann divergence for alpha equals 2 is that it first up and bounds the KL divergence, and the quantities coming from quantum relative entropy. But and it is also much simpler to compute because both the data and the model are now inside of the logarithm. So we don't have to do some complicated logarithms of matrices. We will only do always logarithms of numbers, which very much simplifies any computation. So you can now formally take the derivative if whether you parameterize sigma or rho and get a nice closed form. However, it should be stressed that for this Rayleigh divergence, if you switch the order of sigma and rho, you will end up with a different expression. This is Rayleigh divergence is not a metric because it's not symmetric. However, in our case, it doesn't. If we assume that both our data and the model are full rank, if we switch the order, we will also if we switch the order of our sigma and rho, the data and the model in the formula for Rayleigh divergence, we will still, after the minimization procedure, arrive to the same point because Rayleigh divergence is 0 if and only if rho is equal to our sigma v. So the data is the same as what our model will give us on the visible unit. And similarly as for KL divergence, we will be computing only the gradients, never the objective function. Evaluating Rayleigh divergences is computationally very expensive, but if we look at the gradients, there will be some cases where we can efficiently evaluate them through sampling. And by this I mean that this can be done in a polynomial time, even though you might need a fault-tolerant quantum computer or a quantum computer that would be significantly bigger than what we have now. The key trick we are using in our algorithm is extended swap test. So this trick combines the swap test with the Hadamard test that you probably both know from an introductory class in quantum algorithms. An extended swap test would allow us to estimate a trace of an any product of unitaries and density matrices. So for example, if we have some polynomial in density matrices or some terms that also involve unitaries, the extended swap will tell us. And you can see that in our gradient terms, we will have some, lots of traces that will encode unitaries or Hermitian matrices that can be decomposed into LCU and some density matrices. So we apply our techniques on learning thermal states. Thermal states are in some way easy because if you work in a lab, you will know that pretty much everything thermalizes at all times. However, thermal states can be very, very difficult to prepare as well because thermal state preparation can be seen as a generalization of ground state preparation, which we know is a QMA complete problem. And depending on the formulation, the sampling from thermal states can also be seen as Sharpie hard. So even though creating thermal states can be very, very hard, the thermalization takes place naturally for many cases, especially if we are interested in the higher temperature regime. So let me just give you a glimpse into our generative algorithms to thermal state learning. When I talk to our general algorithm that uses the extended swap test to estimate gradients of Rayleigh divergence, we had this one term that include an inverse of the data, and this is possible to compute with a fault-tolerant quantum computer, but it requires a lot of resources. If we work with thermal states, we don't really need to have the thermal states prepared as training data, and we only need access to the Hamiltonian, then in this case is given to us as an LCU, as a linear combination of unitaries decomposition. And the cool thing here is that first, we don't really need to worry about computing some inverses of density matrices. And second, to estimate the gradient, at no point we would need to compute the partition function of our thermal state. So this is, a thing that computing partitions functions is computationally difficult, but in our gradient computation, they will all cancel out. So we still have some hope that these algorithms could be efficient. We gave two different algorithms. I would stress that neither one of them is very nisky, but we have an algorithm that is quite shallow. It uses sampling to compute the gradients, or you can use fancy tricks such as amplitude amplification and linear combination of unitaries that construct an algorithm with better complexity to evaluate the gradients. In our shallow algorithm, we will have several components. We will start by creating two copies of quantum neural networks on two registers. Then we will have to apply some conjugations of our, of terms. This is just a very technical part that you don't need to worry about. And towards the very end, we will perform the extended swap test that I talked about. In the fault-tolerant algorithm, we use many of the techniques from our shallow algorithm, but now instead of sampling out of many different terms, we will create a coherent superposition across all the terms. And instead of estimating the amplitude by sampling, we could use amplitude amplification that would give us quadratic speed up. For this algorithm, we can compute the complexity of computing a single gradient and show that if the temperature is high enough, if the temperature of the thermal state is high enough, then computation of the gradient will be efficient. And we also have some rigorous results showing that under certain conditions, these gradients will be bounded away from zero, which means the gradients won't be exponentially small, and we won't find ourselves in a barren plateau. We looked at training. We looked at learning thermal states previously, and quite often one would run into a barren plateau immediately when increasing the number of hidden units. But in this case, the numerical results agreed with our theory and show that as we are increasing the number of hidden units, our algorithm, sort of as expected, as you would like it, is getting a lot more better. So with more hidden units, we are getting a much better approximations. The fidelity increases, the loss function decreases, and we keep learning. And so this is all really good news. Of course, our numerics is fairly small, and it's not really fair to try to generalize from a system using 3 hidden units to a system that might use hundreds of hidden units. But this type of numerical results support a theory in our paper. There are also many other questions that we didn't answer. For example, even though we show that our algorithm avoids some barren plateaus and the assumptions behind them, there might be hidden barren plateaus that cannot be prevented. It would be nice if we could apply our algorithm or a version of our algorithm in a Nisky way. if there was if we had an algorithm that would be noise tolerant, this would mean that we would be able to train quantum neural networks using Renyi divergence much faster. There are also many questions we weren't able to answer about conversions, and it would be we were wondering about better characterizations of what states can we learn on a quantum computer, either using Renyi divergence training or different types of training. So to summarize, the take-off message for all of you is that when we construct some quantum machine learning model, trainability should be the first thing in everyone's mind. And it's very important to construct a QML model carefully, otherwise one would likely run into a barren plateau. So thank you very much, and I'm happy to answer some questions.
Excellent, Marika. Thank you so much for the great talk. I was paying full attention, I will confess. Really fantastic. Always happy to learn many things. I'm going to just shoot one question from the start, and we may want to use your slides. Could you comment a little bit more on this extended swap test? This is a technique that I'm very curious to maybe master, and hopefully our audience as well.
Yeah, absolutely. So oops.
Sorry to put you in the spot to switch.
That's all right. Okay, yes. So we have the swap test when we would have generally 2 copies of quantum states, and we would be looking at, and swap test then allows us to compute their overlap, and we also have the Hadamard test that allows us to compute the real part of expectation of the real part of a unitary in some state.
Yes.
So there is one generalization of swap test already, where instead of working with 2 states, we can work with an arbitrary number of states. So this is the second part with all the swaps in here.
And the swaps are then happening like nearest neighbors sequentially?
Yes.
Right?
Yeah.
Okay, got it.
Yeah. So you would order your density matrices such that you only need to do nearest orders. So now you can look at this expression up here with the trace and just set all the unitaries to be identity. This would be what people usually call extended swap test. The other name for now, this monster that my colleague suggested is Swapamart.
The Swapamart?
Yeah, because we also have the Hadamard test that is very underrepresented in this name.
I'm actually going to ask what people think of Swapamart as a name. If you have any comments on chat, let me know. Yeah. I laughed for real, so I like it. Okay. Thank you, Marika.
Yeah. And so, in our case, so we are not only doing a swap test, we can also compute products of not only quantum states, but also unitaries.
Yeah.
And if you look at the extended swap test from the point of linear combination of unitaries, so we can write any Hermitian matrix, any Hamiltonian, as a linear combination of unitaries. Extended swap test also gives you a way to compute expectation values of product of Hermitian matrices and density matrices.
Got it. Thank you. I just thought this would be useful for all of us. Certainly for me, it has been. Marika, I often think about like what variational quantum algorithms have done overall for the field, right? I definitely understand a lot of its benefits, but I do think that one issue with them is that they have potentially fooled us into thinking that quantum algorithms can be a bit too simple, right? A bit too simple. And so I interpret a lot of the work that you're presenting here by adding the fact that if we get more sophisticated and we have more like technical mathematical insights, and maybe allow ourselves to think of potentially more complicated circuits, then there's a lot of benefits that potentially can be reaped. So I was wondering if you could comment on the role that you view that kind of advanced mathematical principles can play in our understanding of quantum algorithms, and maybe comment
Yeah.
on the relationship between math and computer science quantum algorithms.
Yeah, so variational algorithm has been like the entry drug into quantum algorithms for many people.
Yeah,
So their advantage is that they are the vanilla VQE is very easy to understand, and you can also implement it even today with current hardware. However, we already know that they will be very, very difficult to scale up because you would need a lot more measurement. The shot noise that arises in VQE is really a big problem.
Yeah, measurement
and
problem.
Also to have some useful ansatz, the circuits will become quite deep very quickly, and that becomes a problem for noisy quantum computers. And also, once you have deeper ansatz, you have more parameters that you have to optimize. There will be barren plateaus coming up, and there's a lot of problem with variational algorithms. And the nice thing about math and the techniques from computer science, that you are able to on paper see all of these problems coming up even before you ever run a VQA algorithm. So I think learning about VQA is a great way to get a first taste of quantum algorithms and working with quantum circuits instead of just, let's say like a Python script and erase variables as you would be used to from regular programming. But quantum computing doesn't end with VQA and QAOA. People worked for, last more than two decades now to come up with cool tracks and really useful techniques based on Grover search, quantum Fourier transform, recently QSVT, quantum singular value transform, that can be very, very powerful. And just for the people coming in quantum, just don't constrain yourself to just variational algorithm. There is much more out there.
Yeah, and it's maybe not even variational versus not, but it's about like being more comfortable with sophistication is the way that I would phrase it, right? And sometimes you do need to get into something a bit more complicated to reap the benefits.
I mean, knowing more and trying more things can be only useful.
Exactly. Marika, I noticed that you use this language of hidden units and so forth, which I always associate with Boltzmann machines, right? Mm-hmm. And in fact, you're arguably one of the first people to ever work, maybe even like co-inventor of quantum Boltzmann machines. It's a great paper from you, I think, in 2017. Maybe can you tell us a little bit more about what got you initially interested in asking these questions?
Yeah, so in 2016, 2017, QML was a very different world.
Yeah.
It was mostly dominated by HHL algorithms.
That's right.
And there was this really cool paper from folks from D-Wave, but where they were looking at classical data, and they were trying to model it with some quantum version of a Boltzmann machine. So the very nice thing about Boltzmann machines is that they the intuition behind this ML model is very much based in physics. You talk about energies and thermal states. And right. All of these concepts translate really, really easily into the quantum world. However, what becomes difficult is the training part. So even though you can easily define a quantum Boltzmann machine, but saying like, okay, instead of a number, we will have a matrix. Instead of energy, it will be Hamiltonian. 0 and 1 becomes a qubit.
Mm-hmm.
But if you then want to do the same calculation for gradients, you will run into massive issues. The formula for gradient won't be even closed. You'll end up with some nasty integral with some matrices. So that was something we were struggling with Nathan over one summer. And we were also really striving to create an algorithm that would able to learn from quantum data or a quantum data set. So what we were thinking a lot back then is what is a quantum training set.
I see. Have you answered that question now?
I think people became much more comfortable with it, and so you can always work with. So one thing is that you can encode quantum classical data into quantum states in many different ways.
That's right.
You can always encode a probability distribution into a quantum state, but the encoding itself might be quite difficult. You can also work with density matrices that has some advantages. But I became a lot more interested about learning just directly from quantum states and quantum data. If you have some quantum states that you created, let's say, as a solution to your differential equation, you are still not able to read it out from your quantum computer. But maybe you are not interested in knowing all the amplitudes, only in some broader characteristics of the solution. And in these cases, a quantum machine algorithm can be very useful.
Got it. Thank you, Marika. Maybe switching gears a little bit now. Like I mentioned in the intro, you did a joint PhD across two institutions, right? In fact, halfway across the world from each other between Canada and Australia. Do you mind sharing with our audience what that was like and what prompted you to do this?
So I tell people that I was too cold in Canada, which is why I moved to Sydney. And that was definitely a strong benefit of moving there. Also, I was in IQC at the time where not many people did algorithms there. This was before David Gossett arrived.
Mm-hmm.
But the real reason was that my husband, who was a PhD student at IQC at the same time, just graduated, and he got a postdoc position in Sydney. So we were trying to figure out how to solve the two-body problem, while how to stay together and both be in academia. That can be quite difficult, but fortunately, it worked out extremely well for us.
Yeah, I'm very happy to hear that. I didn't know that was exactly the reason, so thank you for sharing that. Marika, before we take some questions from the audience, I hear you love rabbits. Can you tell us more about it? They're just fluffy and beautiful, or what is it?
Yeah, they're fluffy and beautiful, and I eat vegetarian food. So, and if you have a cat or a dog, it's probably a good idea to give them some feed. But if you are veggie, you can eat your salad and make the same version of the salad to a rabbit. And
so you actually have do you have rabbits at home?
No, unfortunately. I fostered rabbits when I was a PhD student.
Oh, wow.
So for those who can't really commit to having an animal across many years, there are often pets that don't do well in shelters, and shelters are looking for people who would be able to accommodate an animal for a few months. So I was a foster mom to two beautiful rabbits during several months. But right now I'm living in a building that doesn't allow pets. Even though, rabbits, they're completely quiet. So your neighbors would never know about it. And if you clean their litter box, they're also very, very hygienic. They don't require that much care.
Nice. Well, that's really good information that makes me maybe want to consider having a rabbit myself. But our dog wouldn't like it. I don't think that would be a disaster. Marika, so maybe some questions from the audience. So a question from Marco DND. That's Marco Cerezo. And the
Hey,
question is,
Marco.
besides the case of thermal states, where the form of the maximal Renyi divergence becomes more manageable, can we expect this method to be used in near term and in more general applications? So besides thermal states.
I mean, even with thermal states, this is not super near term. And more generally, so the problem with with the general formulation is that in somewhere the inverse sneak in. So in some cases, you might be able to use a pseudo inverse or have data that you can invert directly. And we know that there are some cases where this happens. But for most cases, it would be quite difficult. There is a way to compute inverse for low rank matrices or sparse matrices with HHL, which is efficient, but you would probably need a fault tolerant to do it. Fault tolerant computer.
Got it. Thank you so much. And I guess maybe last question before we wrap up. This is more of I guess, curiosity, and then maybe a good opportunity for people to learn about this. So I'm sure you know the answer, but are there any classical analogs of the quantum Renyi divergence?
There's classical Renyi divergence.
Yeah, maybe can you comment a little bit on that, maybe for the audience? What are they used for? What role do they play? How do they look like?
Yeah, so when you're studying, information theory, there is a lot of generalizations of divergences and entropies that will all apply different noise for like even a lot of data or finite amount of data. I'm not really an information expert, but this is a really cool area that is very, very beautiful mathematically.
Yep. Absolutely.
Do you have something to add, Miguel?
No, I mean,
yeah.
I think you said it correctly, but I do know that there's a zoo of entropies, right?
Yeah.
And that's with good reason, in the sense that oftentimes there are different things that you want to quantify in a system in different scenarios, and oftentimes there's like an appropriate measure to do this, right? I know at least people working in information theory, they discuss operational interpretations, right?
Yeah.
And they also talk about different bounds. And so Renyi entropies are kind of a way to interpolate a family of potential different measures that each have kind of their own suitability. And you can get even fancier as well. So actually, in general, it's an example of how even seemingly innocuous questions, right? Like how do I quantify how much I'm learning from a system? Can take on different versions, right? And so definitely a lot of smart people have been working on this for a long time. But I would argue the question is kind of the opposite, right? So there's the classical divergences are the ones that have been studied a lot, and there happens to be a quantum analog of it.
Yeah. Yeah, I think at this point, both classical and quantum have been quite studied.
Yeah.
You
definitely
can, you look at the information in classical system and in quantum system, and there are some important differences in understanding them. Is I think just really fascinating.
Yeah, and for the audience like this was a talk that I would argue introduced a lot of techniques, a lot of tools to use, right? And so the Renyi entropies are one example of that, right? It's a good thing to have in your arsenal that potentially be like, oh, what if we use this measure instead, right?
I think just the question of what measures should be what measures and what objective functions are the right to use for learning. Fidelity is very common, but
that's right.
Using fidelity has some very, very important problems.
Exactly. In a way, that's the main conclusion from your talk, right? Is just think differently about cost functions. I love, for example, the fact that we can train models without computing the cost function. And it's true, right? You only really have access to the gradient. So what changes if we allow ourselves models where maybe the cost function is complicated, but we have access to the gradients, right? So a lot of progress can be made thinking even about something as potentially simple as what's the right cost function.
Yeah, these simple questions tend to be quite hard in QML.
Yeah, and maybe even more generally. That's right. Marika, that's basically the time that we have for today. Thank you so much for joining us. It was really great having you. And yeah, enjoy the rest of the day. Enjoy sunny California.
Thank you for having me. This was fun.
Yeah, absolutely. Always nice talking to you. Have a great one.
Bye.